Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'm revisiting a question I recently worked through that related to hexagons. So it was a question aimed at Year 6 students in the context of a scholarship application for a private school. And ultimately, the question involved a shape that was ever expanding, comprised of more and more hexagons. And ultimately, the question wanted us to work out a way to count the number of unique edges in that shape. And if you haven't already seen it, I'll provide a link to that video where you can take a look at the background to the question and how I worked through it. And at the end of that video, I put a bit of a call out to anyone who might have some alternative ways to tackle the question. So in this video, I'm going to work through one of those ways, and in this particular approach came from another of my Master of Teaching colleagues, V, who spotted another pattern that you could make use of. So the approach I originally used ultimately just made use of a pattern that I noticed, and V noticed another pattern, and I think it actually leads to a bit more of a efficient solution. I think there's a bit less counting required in this approach, so I think it'll be a good one to work through. So here I've set up a table, and this is how we'll structure our thinking here. I've actually got my original working that we can reference. So my original approach looked at the number of unique edges, and the pattern I looked for focused on the increase in those edges and the second order increase, or the increase of that increase. For this approach, I've defined some variables, I guess we can call them. The first one is Hn, which is the number of new hexagons at each expansion. And then Sn is the number of new sides for each expansion. And then Tn is just the running total of the number of sides. So ultimately, T20 is what we want to work out. And if we come and take a look at my original approach, what we're looking is a T20 of 3,421. So maybe I'll just note that. We want to get to a value here that's 3,421. And actually, if we do get that, that provides a bit of comfort that my approach actually is correct, because I don't really have a way of verifying it. I think it makes sense, but it's always comforting if you can find alternative approaches to get to the same answer. So this is how we'll structure our thinking. I've gone ahead and drawn up the first few expansions. So we start off with one hexagon. So in this case, at n is equal to 1, the number of new hexagons is 1, because we're starting from nothing and we add 1. The new sides would just be 1, 2, 3, 4, 5, 6. 6 sides to a hexagon. And the running total would also be 6, because we've again started from nothing. Now with the second expansion, what we did is we added 1, 2, 3 new hexagons. Now the number of new sides here would just be these extra black sides. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 new sides. And so the running total would be 6 plus 13 equals 19. So hopefully that structure makes sense. So now what we'll do is I'll expand, I'll do a few expansions, note the pattern that V spotted, and then we can see how we can use that pattern to fill out this table. So the key to this approach is, I might just go to red, is as I'm drawing the extra hexagons, what I'll do is I'll note the number of sides that I've drawn for each hexagon. So if we start from here, I'll have 1, 2, 3, 4. So I had to draw 4 sides to add that hexagon. And then 1, 2, 3, 4 again. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. And then 1, 2, 3. So that's the expansion. In terms of the number of new hexagons, we've added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 new hexagons. So I'll just note that down, 10. In terms of the number of new sides, well, instead of manually counting them, because I've noted the number of sides I've had to add as I've gone along, we can just look. So we've got 1, 2, 3, 4, 5, 6 of hexagons where I had to draw 4 sides. So I could write that as 6 times 4. And then the number where I've had to add 3 sides was 1, 2, 3, 4. So we'll have plus 4 times 3. So I'll just get my calculator to plug that in. So if we go 6 times 4 plus 4 times 3, that's 36. And if we then get our running total, so if we add 19, we're at 55 as a running total. So now what I'll do is I'll do another expansion, and let's see if we start to notice a pattern in the number of new hexagons and number of new sides. So let's come, and I'll come back. I'll stay on blue. So here we go, 1, 2, 3, 4. 1, 2, 3. And then 1, 2, 3. Alright, so number of new hexagons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 new hexagons. And then in terms of how many hexagons needed 4 new lines, 1, 2, 3, 4, 5, 6. So 6 times 4 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 3. Now, here's where we can start to think, okay, are there patterns emerging? First, notice in our new sides, the 6 times 4 didn't change. But in terms of the number of new sides that required 3 lines, we needed 10, and 10 happens to be the number of new hexagons from the prior expansion. So that's something to keep an eye on. And also notice that the number of new hexagons grew by 6. So is that something that's also going to be consistent? So we can keep an eye on that as we do our next expansion. But for now, I'll just plug this into my calculator. So 6 times 4 plus 10 times 3 would be 54, plus 55 gives us a running total of 109. So now I'll just do the next expansion. So let's come to black. So 1, 2, 3, 4. 1, 2, 3. One, two, 3. Alright, so let's count number of new hexagons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So let's note that down. We've had 22 new hexagons. How many of them needed 4 lines? 1, 2, 3, 4, 5, 6 again. So 6 times 4 plus how many needed 3? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 3. And notice we've grown our new hexagons by 6, and the number multiplying by 4 stayed the same, yet the number multiplied by 3 was again equal to the new hexagons from before. So I think that's, looking a lot like a pattern. And this is where we could expand that pattern and see if we get to the same result that I got using my other approach. So I'll just key into the calculator the running total that we're up to here. So 6 times 4 plus 16 times 3 is 72, plus the 109 gets us to 181. So we're at 181 at the 5th expansion. Now, we have the luxury here. Can we go check what my approach had at the 5th expansion? 181. So that should give some confidence that this approach could be workable. I guess if we didn't have the luxury of my prior approach, we'd probably want to do one more expansion just to really confirm this pattern. We've had 2 growths of 6, we probably want to do one more to get 3. But just because I kind of know that we're on the right track, I'm just going to go ahead and assume there's this pattern and see if it gets us where we need to get to. So I won't need to draw much more. And I mentioned at the beginning, I think this approach is a little more efficient. And the reason I say that is because so far we've had to count hexagons, but we haven't really had to count one at a time all the extra lines, all the extra edges, like I had to do with my approach. So it's a little bit faster in terms of just the kind of mechanical, mundane counting that you have to do to establish your patterns. So that's why I like this approach. I think it's that little bit quicker. It's a little improvement on what I did. So let's just go for it. So let's expand or complete the first column, and we can do that just by continually adding 6. So if we take out 22 plus 6, okay, 28 plus 6, 34. And then 112 is the number of hexagons that we'll end up with at the 20th expansion. So that's column 1 done. Now let's work out column 2. So we know it's always going to be 6 times 4 is 24. So it's going to be 24 plus, in this case, the prior new hexagon, so 22. So 22 plus 24 plus 22 times 3. So 24 plus 22 times 3 would give us an extra 90 here. So I'll just note down the 90. And let's just carry on and fill out this table. So and then 24 plus 106 times 3, 342. Now, you may have noticed in the process of me doing that each time the number of new edges was jumping by 18. And that is no surprise because each time the new hexagons is jumping by 6, and we're only changing the number jumping by 3, and if we've got an increase of 6 times 3, that's always going to be 18. So the new edges is always going to grow by 18. 18 is the second order increase that I had noticed at a pattern. So it makes perfect sense that these two approaches will get to the same result because they both ultimately end up kind of having an increase of the increase of 18. So this is just another way to get there. And as I've mentioned a few times, I think a little bit more of an efficient way because the kind of brute force counting was a little bit quicker here. So now all we have to do is get the running tally and confirm that we do get to the right answer. It should be no surprise that we will, but we should probably do it just for completeness. So 181 plus 90. Plus 342. 3,421. So we get the right answer. And again, it shouldn't be much of a surprise. But really, really comforting to see that through a different approach, we can get to the same answer. And again, what V has done here is she spotted a pattern that at the end of the day, fundamentally, this is a question that tests the students' pattern, I guess their ability to notice patterns. Given they're Year 6 students, you probably wouldn't expect them to be able to write out the formula. But if you were interested, one way you could represent this is you could define it using recursive formulas. So you could kind of start by saying at any expansion, Hn will equal to, it'll be equal to the prior Hn. So you could call that Hn minus 1 plus 6. So our Hn is always increasing by 6. And then for Sn, you could say, well, the Sn at any expansion is equal to 6 times 4, and I'll just write that as 6 times 4, plus, and again, we look at the prior Hn, so Hn minus 1 times 3. And so with these two recursive formulas combined, we can end up getting our running total, because Tn is just the sum, the kind of sum of all the n's prior. So again, you wouldn't expect a Year 6 student to necessarily have the tools in their toolkit to represent it in this kind of recursive way, but that is ultimately what they're doing when they kind of work through a table like this. You'd hope that well, actually, I think they'd have to have some way of structuring their thinking. Probably a table is the most natural way to lay this all out. It would be kind of a bit hard to keep it all in your head to kind of get to this answer without kind of breaking it up into steps. So I think it just makes sense to kind of structure your thinking in a table. So as I mentioned in the prior video, if there's a Year 6 student out there who kind of gets this, I think, yeah, they're doing very well. I think it's a very difficult question for the Year 6 level, so it kind of makes sense why it's sitting on an exam that's kind of, the purpose of the exam is to kind of hand out scholarships, so it kind of makes sense in that context. So there you have it. Thank you to V for sharing your thinking. Hopefully that's kind of perhaps inspired some people to think of even more ways that you could tackle this question. If you found that explanation helpful, please be sure to give the video a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. All right, tick boom.